Alright, so looking at our first two now problem, we're looking at this and we know that in order to use our any order, any grouping, our combination of commutative property and associative property, that we do need to change everything to addition first. So I changed this one to change it to add the opposite. And here when I change this to add the opposite, it's the opposite of this group. And we know that in order to get the opposite of a group, we need the opposite of every piece of the group. We can also think about it as a distribution of -1. So -1 times would give me the opposite, which is 4g, and the opposite of +2, which is -2. Bring down the rest of this 4f plus -3 plus 2g. Want to go ahead and commute all my like terms next to each other, so I can combine them. 4f plus -3 plus -2 plus 2g plus 4g. 4f is not a like term with any other term, so it cannot be combined. -3 plus -2 is -5, and 4g plus 2g here gives me 6g. So looking through at our answer choices, that looks like that appears to be answer choice E, none of the above. Only one of the answers has a +6g, and that one has a -1 instead of a -5. Again, remember we can always change these add opposites back to subtractions if we want to. And that's the form that they've taken here in the simplest form. So remember, standard form, same thing as simplest form. Flipping over to our other problem, it says rewrite it in standard form. Remember that we can rewrite every division as a multiplication. So we have this 27h times its reciprocal, 1/3h. So by multiplying by the reciprocal, in this particular case, we're taking 3h/1 becoming 1/3. Multiply top times top, bottom times bottom gives me 27h/3h. Well, we see that h/h, that's really just a multiplication of 1, which gives us 27/3, which is equal to 9. Alright, let's go ahead and look at our aim for today. Alright, today's aim, Kipsters will be able to use area models and distributive property to write out the sum of products, and also kind of do the reverse as well, which is to write the products of sums. And so what we're going to be looking at when we do this, we're going to be looking at just diving deeper into distributive property, seeing some different ways that we can visualize distributive property and use the algebraic method as well, and kind of putting those two side by side to see different ways we can think about the distributive property. So as we come down, just to get our brains going about what some of these visuals look like, we're going to use a tape diagram. It tells us the sum of money is shared between George and Brian is in a 3-to-4 ratio. So you can see our tape diagram has 3-to-4 for George, and I put Brian in one place and Benjamin in the other. Brian, if the sum of money was $56, how much did George get? So we can see that the sum of these two tape diagrams is going to be $56, and we know that it is a 3-to-4 ratio. So we know that there are 7 total parts, so 7 is equal to $56. So 7 times x. We'll call each of these pieces 1x because they're all the same. I've just broken it down in 7 parts. So 7x is equal to 56, which tells us that x is going to be equal to, as we divide by 7, x is going to be equal to 8. So this is 8, and 8, and 8, and 8, and 8, and 8, and 8. So we can see that Brian is 4x, or 4 times 8, which would be 32, and George would be 3 of the x, which is 3 times x, which is equal to 3 times 8, which is 24. So how would I represent 3 plus 2 on a tape diagram? So this is kind of just getting us started in thinking about tape diagrams, because we're going to be putting tape diagrams together. So we have 3 plus 2, we could think about it as 3 plus 2. And we can also break it down thinking about it even more specifically is like this part is 3, this part is 2, so this would be 3 plus 2. Alright, so represent x plus 2 on a tape diagram. Well, it's the same idea. We have this part which is x plus 2, or we can break down that part that we can see a little bit more clearly into two pieces, where this would be x, this would be 2. Both of these function the same. So draw a rectangular array. So this is where we're thinking about the sides of a rectangle being two different pieces. So here I have a rectangle, and I have this part is 3, and then on this side we have 3 plus 2. So I'm going to cut it down the middle. This is going to be 3. This is going to be 2. So this is 3 plus 2, running the length of this. And it's a product, and the reason we use a rectangle for that is because we think about area of a rectangle is length times width. So if I have 3 times 3 plus 2, it's kind of like thinking about the area of this rectangle. So we can think about the area of this rectangle very visually as the area of this portion plus the area of this portion. So that would be the total area of the rectangle. So when we see this process and we think about it, now we can see, looking at this particular diagram, if I just break this down even further, just thinking about this was 3 long and each of these was 2 long, then I look at the areas, this is broken into 3 holes as well. I can see the area of this portion is 9. The area of this portion, oops, this one should have only been broken down into 2 pieces. Fix that up just a little bit. Broken down into 2 pieces, so the area of this one is 6, so that's 9 plus 6. And we can see again that mirrors what we do with distributive property. 3 times 3 is 9 plus 6. So we want to draw a similar array for 3 times x plus 2. Well, we have one side of our rectangle, which we'll label as 3. The other sides of our rectangle, one of them is going to be x, this unknown length, and the other one is going to be 2. So if we think about this, this is each of these units broken down into 3 pieces. This one's into 2. And so each of these is 1 times x. So it's kind of like thinking about this as 1, 1, and 1. 1 times x, which is x, x, and x. And then looking at this whole chunk is 6. So we have the 3x's, or this whole piece we talk about is 3x plus 6. So we can use these diagrams to kind of help us figure out and think about different ways to think about these different uses of distributive property. So coming over here, determine the area of each region in the distributive property. Go ahead and do that on your own. So you should identify that this is 176 and 55. Do me a favor, off to the side, right here, what this would be in terms of what is this rectangle, what multiplication of a number and a sum is this trying to model? So hopefully you're thinking about it as, what are my sides? Well, one side is 16 plus 5, 16 plus 5, and that's times the 11. So this is what this is trying to model, and we can see that if we use the distributive property alongside that, we see this is 176 plus 55. Alright, for each of the problems below, I want you to go ahead and model each of these expressions using a tape diagram. So go ahead and do this in pencil. Work with your partner to jump through these four to see how you can model them with tape diagrams or arrays. And if you get stuck, move on to the next one and we'll try and come back to it when we get a chance. So as we look at this first one, this one is going to be x plus y. So this would be x and y. And we have three of those pieces, x plus y and x plus y. So that's one way to represent that one. X plus x plus x, so that would be in parentheses. So we can see that when we have these bars, when we have these groupings, we're kind of modeling them as single chunks of bars on their own. Now as we get down to this one, this is the one that I think seems interesting to some of us. We have 3x, so plus 3y, so we have 1x, 2x, 3x, x, x, and x, and then we have three pieces of y, 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 and y. But alternatively, I think some of us recognize that we could go ahead and break this one apart after looking down at the next one, that we could write that one somewhat differently, because we can model this one with the area array, where this is x and this is y. So this would be 3x and this would be 3y. So we can see that's the same thing, 3x plus 3y, as this model over here could be modeled the same way. So we can see that sometimes these area arrays can help us kind of determine the different ways to model various different equations. So what can we conclude about all of the expressions? Well, if we start to look at it even more carefully, this is 3x plus a 3y. This one is rearranged also the same way, would be 3x plus 3y. So you should be identifying that all of these equations are equivalent. How does the 3 times x plus y, how does the last one equivalent to the one before it? How is h equivalent to g? And we can see that in both cases they're just three groups of x plus y. And in one way they're modeled together, in one way that they're not. So when we look at this and we just think algebraically about them, the one thing that we will say is this is the standard form or the simplified form, and so that may have more significance or more use generally in the real world. Under which conditions would each representation be useful? So thinking about that is, well, usually a lot of times the simplified form may be the most useful, but sometimes I look down in here and when I see x plus y, if those are going to be compatible numbers that maybe add up to a multiple of 10, it may be easier to add the x plus y together first. And so it's really important to be able to identify that there are different options here. Which model best represents the distributive property? I would say probably our last model represents distributive property best. Alright, let's go ahead and move on to the other side. Alright, here we're being asked to find the equivalent expression by modeling with a rectangular array and by applying the distributive property. So over here, I want you to show me what the array would look like and how that helps us determine an equivalent expression. And over here, I want you to use your algebra using the distributive property that we already know. So go ahead and take a moment, pause the video, and do both representations. So I've gone ahead and set up my array over here. I on one side have the 5, which is being multiplied by the length of 8x plus 3. So I've got my array broken down. The area of this one would be the 5 times 8x, which is 40x. Oops. 40x and the 5 times the 3, so the length of this side is 5, this is 3, that's why the area of this particular portion is 15, and so we would get the expression that the area, or the multiplication of these two things, 40x plus 15. We do the same thing over here with the distribution. 5 times 8x is 40x, plus 5 times 3 is 15. For the next 4 problems, so we'll just say for parts A, or these are labeled funny, for parts D through G, I want you to go ahead and solve each expression using the array and the algebraic method. So again, this is going to be a little bit more practice showing the array method and distributive method using algebra. So go ahead and jump through these problems and then come back and we'll check. Alright, let's go ahead and look at these solutions. Now, particularly once you've checked over these, I really want to talk about F and G, these last two. Looking at the physical models, think to yourself, what's a little bit strange about these physical models? What doesn't really make sense for us in the real world if we're actually talking about areas of shapes here? Hopefully you're identifying amongst yourselves that these negative areas don't really make sense. You can't have a negative space in the real world. So those don't really make sense. And that's where our physical models kind of start to break down sometimes. So that's why we definitely want to have our algebra skills available for us in order to do some of these problems. Let's go ahead and slide over to the next couple of problems. Alright, so this one asks to rewrite each expression as a sum. So the reminder here is, as we're looking at these are each divisions, and we know that we can rewrite each division as a multiplication, so we can use the distributive property. So what I'm going to do here is I'm going to rewrite each of these as a multiplication first, reminding me that I'm going to change this to multiply by the reciprocal. The reciprocal of 2 over 1 is 1 over 2. So it's 2b plus 12 times the reciprocal 1 over 2. So I'm distributing in this multiplication of 1/2. So I have 1/2 times 2 over 1 times b plus 1/2 times 12 over 1. That's 2 over 2b plus 12 over 2. Well, that's really just 1b, which is just b, plus 12 over 2, which is 6. All right, go ahead and do the next two on your own, and then pause the video and then come back. And once you finish those two, we'll check over your solutions. All right, quick check on those two solutions here. Again, we see that we have changed the division to a multiplication of a reciprocal and distributed it in as a multiplication of a fraction. All right, the last two pieces we want to look at for today. I want you to see if you can create what a model would look like, an area model would look like for this this expression, and then go ahead and find me the simplified distributed version of that expression. So we can see that it's 4 times this group, so this group is going to be one part of our rectangle, and the other side is going to be 4 units. If we break this down, we have 4 different areas to find this. This is 4 times x, this would be 4 times y, and this would be 4 times z. So our total area, or our simplified expression, would be 4x plus 4y plus 4z, or algebraically, we could have seen that that was 4 times x plus y plus z by thinking about our distribution, 4x plus 4y plus 4z. And finally, I'd like you to do the same thing with this one. So as we come back to this one, thinking about using the distributive method, multiply in, 3 times x would be 3x, plus 3 times 2y would be 6y, plus 3 times 5z would be 15z. Thinking about what the area model would look like, we have a side of 3, then we have one that's 2x, 2y, and 5z. So this would be 3 times x, 3 times 2y would be 6y, and 3 times 5z would be 15z. All right, go ahead and move on to your alone time, get those problems done, and we'll get some results here at the end of the period.